This is a brief explainer video about our recent paper, The Tangled Warp of the Milky Way. This is work that was led by Victor Janssen when he was a master's student at Lund University. I'm Paul McMillan. I was supervising him during that project, and I'm now a lecturer at the University of Leicester. Our starting point is that the Milky Way is warped. The Milky Way is a disk galaxy, and that disk is flat in its center, but then in the outer parts it warps upwards on one side and downwards on the opposite side. This is something that we didn't discover in this paper. This is long known. It's been seen in both the stars and the gas. I rather like this illustration by Murch and Fan from a paper just last year, where they show the positions of gas in the galaxy in terms of is it above or below the flat plane towards the center of our galaxy. So here they're coloring red for above the plane and blue for below the plane. So with the sun being positioned where that arrow is, we can see that the gas on the left-hand side of this image, which is the direction in which the sun is rotating in that direction, as are the stars, as is the gas. We can see that on that side the galaxy is warped upwards. On the right-hand side, conversely, the galaxy is warped downwards. So that's the positions of the gas. We would see something very similar in the stars. Now the question is, what about the velocities of stars that we see? So that's what Victor and I did. We looked at the stellar velocities of stars as seen by the Gaia spacecraft and as put in the Gaia Data Release 3. So orienting ourselves again, we have the sun as indicated here, galaxies warped upwards on the left-hand side there, warped downwards on the right-hand side there, and the sun is rotating clockwise as before. So what is the kinematic signature that we see? Well, coloring now by vertical velocity upwards being red and vertical velocity downwards being blue, we can see that as we go outwards from where the sun is positioned, the stars are going upwards as they're rotating towards the clockwise towards where the warp is upwards, and that's what we'd expect naively. But as we go further out, that stops being true, and in fact towards the outer galaxy we see even that the stars are going downwards, though they seem to be going towards the higher part of the warp. That doesn't make much sense intuitively. So we have to try and understand that. I think we have some toy models that help explain that. So this is one where we have just a static warp. The galaxy is a warped disk and the stars are just rotating within that galaxy. On the left we're showing this as a simple animation from a viewing angle. On the right hand side we're showing it as if we were looking from above and just showing again colored by red or blue the vertical velocity of the stars in the galaxy. And what we see is roughly what we'd expect to see, that as the stars go from the lower part of the warp to the higher part of the warp, they end up with high positive vertical velocity, and the opposite on the other side. What I've also drawn here is what's called the line of nodes. That's the dashed line. That's the point where the stars are going through z equals 0, so going through the plane of the rest of the disk. You might have noticed that that's also where the velocity of these stars is at their greatest, either upwards or downwards. So this was our static warp. But what happens if that line of nodes, if that warp is precessing? Well, then we have something rather like this. Our toy model on the left now has a precessing line of nodes, also shown in the plan view on the right. And you can see that the behavior of stars just into the warp is roughly as we'd expect still, that they're going faster than the line of nodes. So they are heading upwards towards the higher part of the warp or downwards towards the lower part of the warp. But then as we go further out, this stops being as simple. The second outermost ring on the left is actually just going at the same speed as the line of nodes. So the stars are going neither up nor down because they're just moving with the warp. In the outer part of the galaxy, the warp is overtaking the stars, so stars seem to be heading towards the higher part of the warp, but actually the lower part of the warp is catching up with them. So again, we have a view from above on the right hand side, and if you remember what the velocities of stars in the Milky Way look like, you might be seeing a similarity between what I'm showing on the right here and that image, which I've now just overlaid. So we think this explains what we're seeing here. Indeed, we fit a fairly simple warp model to this data. We end up with a precession speed for the warp of 13 kilometers per second per kiloparsec, which other people have found before. This model fits quite well. This is quite a fast precession rate. It's faster than we would usually expect for a warp, but we separate the data out into sort of 10-degree segments here around the galaxy, and as you see, the model fits quite well throughout almost all of the data that we have. What we then have is this line of nodes, this line where the where the warp is going through z equals 0. And that's at around 140 degrees, where the sun is at 180 degrees in the kind of plane of the galaxy. And that's a surprise, because when we look at the positions of stars, that line of nodes appears to be at about 180, very close to where the sun is sitting. So this is an unusual and unexpected result. We also look at how this line of nodes is changing as a function of radius as we go outwards in the galaxy. Again, we have some expectations of what that should be. Unfortunately, the data don't really give us a clear picture of what's going on here. And we can thank our referee for really pointing that out to us, because they encouraged us to look at this more carefully, and we ended up with the plot I'm about to show now, which is showing that line of nodes when we've allowed it to vary with radius rather than simply being radial outwards from the center of the galaxy, and what it is when we consider different samples of stars, where we stop our sample either at 13, 14, 15, etc. kiloparsecs from the center of the galaxy, so all of the stars outwards to that point. And you can see, depending on what we choose, we end up with rather different answers, and it's not in a nice simple way. You know, we get the similar answers when we have 13 kiloparsecs as when we have 18 kiloparsecs, but different in the middle there. So this estimate that we've got purely from the velocities of stars, purely from the kinematics of stars in the galactic warp, is rather different from that of that we find in the stellar positions. That is a robust result, even if how it's changing with radius isn't. So what does that mean? Well, I think this is a real challenge for all of us interested in how the Milky Way's warp formed. It's a real challenge to theorists and people running simulations of this. If your model is supposed to explain the Milky Way's warp, then it needs to explain both a warp that is precessing quite fast and also a warp in which, if we measure the line of nodes from the kinematics, we get a different answer from when we measure it from the positions of stars. I'm really interested to try and work out what that means and what that's telling us about the history of the Milky Way, and I really hope a lot of other people are too. Okay, thanks very much.